Hello, this is Manmeet, and I'm going to go over the introduction and the approaches we used to disassemble the malware sample. We tried various ways explained throughout the semester to get a hold of the simulated malware sample. Let's talk about a few of those first. First of all, we had to execute the file and do the same. To do the same, we set up a 32-bit Linux virtual machine using the virtual box, but it didn't work as it displayed a message, "No VM, please." We were kind of disappointed, but we moved on and we tried a few different methods that we're going to look over now. The first one is scanning. As we already inferred that the malware sample seems to detect VMs, so we switched to IDA Pro and looked at the code in string view, as it is the most convenient method to look at all the weird looking functions. As we were looking at the functions, we soon realized it contained a string saying, "You fool, nobody debug me," which evidently meant we can't debug it, in addition to it being executable on a virtual machine, inexecutable on a virtual machine. Also, it had other strings which seemed of some use, so we jotted it down and traced it functions to look if we could find something interested. Upon tracing strings like "nope" and "good job," we realized that most of the functions within the program loads the address of the string from the specific function rather than being attached solely into the function. Since strings like this are not mentioned in the code directly, we started to analyze what we have in the function directly. The "no VM please" string and "don't debug me" string belonged to a check function. Further down, we found a loop function that checks for a jump condition immediately after the program finishes the loop function and is looped a total of 50 times. The loop loads into a function to apply the XOR operand. We put all the hexadecimals derived from the check function into a C++ compiler and program which on researching and it returned the text lscpu, which on researching a little it verified to be a Linux command to know about the CPU's architecture. So we found out that this is the function to check if the sample is being run in the virtual machine and immediately returns "no VM please." We continued further and addressed its anti-debugger capability, as which my friend will explain.
So next part was getting rid of anti-VM. As we can see, there is a condition added that jumps to a code once it is satisfied. Um, so what we did was we ran a patch. We changed the jump condition initially from JZ to JNZ and saved that assembly code. On saving that, we were able to skip the anti-VM condition. Next part was getting rid of anti-debug. As we can see, there is a ptrace function being called that was preventing us to run the file. To get rid of anti-debug code, we did a similar thing. We also ran a patch and changed the JNS condition to JS, and this was done in a similar way by changing the assembly code and then saving the condition. On running the patch file, we could easily skip the anti-VM and anti-debug condition, which enabled us to move ahead with the project and go to the next part.
After cracking the two protection, we can take a look at the main function, which we can see that it was checking the string length of something and compare it to 0x8, which is 10. So we come to the conclusion that if the password doesn't match the length of 10 character, the function won't actually load into fun to pack and it just exit the function. Now take a look at the unpack function. We see that there's a list similar to the check function, and we can also see that it's calling the mprotect function, which modify the the permission of a memory sub specific memory part. This further back up by the loop in the function, and we can see that it was loading in the address of the fun to pack function. So basically how this program works is it was storing what the address it got from the fun to pack what it got from the fun to pack function with two keys. The first key is 0x9. The second key is based on the list, and it's using um, the remainder when dividing with the loop as the index, so that it doesn't have to use 170 key to sort the the entire fun to pack function. So it just uses the same 10 key over and over again. Then it copy the memory from var1c, which is what the crypt function result to, into fun to pack with memcpi. And it is change the main protect memory back to what its original was. So based on what we found, we can assume that the fun to pack function was decrypted, and we can view its memory by breaking a point after the unpack function was called.
As Lee covered in the previous section, we noticed that func to pack function, and we actually noticed something very interesting about this function. It's that it's almost as if it's not meant to be run in that state. So we found that when we were actually checking the func to pack function, it's not an actual function detected by IDA. And in addition to that, there were many lousy bytes that we found that made it seem like it wasn't meant to be running in this state. So we noticed that if we check this function in the state in our virtual machine, it actually notifies us that a lot of the functions have bad bytes. And in addition to that, the main function needs to run the unpack function before it can call the fun to pack function. So this led us to believe that func to pack, was actually short for function to pack, and that this function is actively being encrypted or packed, if you will, and that the unpack function was meant to decrypt this function before running it. This was further backed up by the contents of the unpack function, and now that we know that that's the case, we know that we have to further investigate the main function and see how those other functions affect the contents of the func to pack function. So now that we've addressed the func to pack function, the main function, the unpack function, the anti-VM capabilities, as well as the anti-debugger capabilities of this program, now we're ready to solve the password. So we went back to the XOR cipher one final time, and where we noticed that it was XOR'd with the value of EBP0x11, if we track this value, we find that the program first moves EBP0x10, which again we established earlier is the loop count to the EAX register. It then adds the 0x804878 address and 0x18b. So it's similar to before, how it was checking with the list of values and moving to the next value from the base address that was provided. This basically meant that EBP0x10 was counting for each of the hard-coded values, and since the loop condition was JLE, jump if less or equal, referring to the value being less or equal to 0x9, it then starts at 0. This means that we'll be taking 10 bytes starting from the address of 0x80478D and adding it to 0 and 0x18b, which finally gives us an address of 0x804918. With this information, we can finally grab our key. So we switched to hex view just to get the necessary bytes, and we took the 10 bytes starting from the address that was first added into the register earlier. So this means that we'll start at character E8, and this gives us the following 10 bytes. E8, 53, FC, FF, FF, 83, C4, 10, 85, and 0. And from there, we XOR'd those characters with the hard-coded encryption that the function provided, of course, skipping EBP0xc because it's empty, and EBP0x10 because we've already identified that to be the loop counter. So finally, we're given the hard-coded hex from the function BC 7A 99 DC 93 BB 83 54 F1 and E1. And if we use the 10-byte hex values from this code and apply it to the XOR operand using the 10-byte hex values, we will get this as our password. So that's a T, right bracket E, pound sign L8, capital G, capital D, T, exclamation mark. And now that the program is providing confirmation of the correct password by displaying good job, we know that we've got the correct password. Awesome.